Так, сегодня ковыряемся дальше. Я купил черную краску другого производителя, Медиколы, немецкой палитры, и она, блин, нормальная. Она черная, немецкого синюшного оттенка, и не надо ничего наводить. Ну и хвала небесам. Вот, правда, она не очень прозрачная, но мне это тоже не нужно. Особенно сегодня чем занимаемся? Сегодня работаем по серому. И нужно вот проработать всяческие места. Не могу понять вообще, эта камера наведется, когда вот навелась. Вот. Короче, я думаю, что у меня минимум 2-3, может быть, еще сессии с этим совсем. И я закончу. Я уже определенным образом вожусь тут. Вот, взял акрил. Это честно нормальный простой акрил. Вот здесь. Убрал. Надо сказать, что это не имел особенно какого-то такого критического успеха. Так, что-то я делаю не так. кажется, даже понимаю, что я делаю не так. У меня слишком зеленый оттенок желтого, который я меняю. Это я болван. Все-таки охру, не хаки. Даже она недостаточно. Теплая. Хотя нет, достаточно теплая. Вот. Давай добавим прямо вот совсем прям бесстыдно ржавчины. Да. Как раз то, чего мне нужно было. Мне не хватает как раз вот на протяжении всего рисунка именно да, вот это вот неприличный ржицы. Так. Это надо прикрыть. Факт, он действительно так, действительно должен быть рыжий. Да. Очень напряжен. Как раз. Тоже интереснее становится. Да, конечно, нарисованы черти как были. Не понимаю, где глаза были у Сумаруковой. Вот. Самый, как мне казалось, проблемный кусок это была вот морда тут. Кажется, я с ней расправиться. Вот. Выражение стало более понятно на морде. Так, ну вот, эй, камера. Не могу понять вообще, эта камера собирается на что-нибудь наводиться нормально или как? Ну, извините. Потом рассказывают стримеры, типа. Вот. Накопим денег типа на новую камеру тогда. И будем париться. другой. Сюда нужна чистая. Хотя бы до какой-то степени, потому что мешают пятна.
same is true for all other observers. That is, all observers can agree on which event precedes which other event and thus causes it. At this point,
Охуенно.
but what about the breakdown of simultaneity? Let's take a look. We start by drawing a space-time diagram with space on the horizontal axis and time on the vertical axis. Suppose that event A occurs at the origin of the space-time diagram. Now, if we were to draw the trajectories of light that are emitted by event A, they would correspond to these two 45-degree lines emanating from point A. This pair of vertical lines is called the light cone. The reason why it's called cone is because if we were to draw this in 3D space, it would look like a 3D cone. Now, any event that happens inside the light cone, such as event B, knows about the occurrence of event A. Therefore, all events happening inside the light cone have causal relationship to event A. This causal relation is true not just for the stationary observer. Here, it's true for any moving observer as well, because at best we would squeeze the coordinate axis towards one of the branches of the light cone, and the causal relationship would not be able to change. Now let's consider event C, which lies outside the light cone of event A. Event C is not causally connected to event A. So the reason for this disconnect is because information traveling even at the speed of light from A would never reach C. The only way information about A would possibly reach C is if it travels faster than the speed of light. So what we are going to do now is think about the consequences. Let me go ahead and declutter the picture very simply and then drawing the coordinate system for a rapidly moving observer that is moving at roughly half the speed of light. So after struggling with the drawing software, here is the coordinate system. The time-like axis corresponds to the motion of the satellite starship. The other axis corresponds to the space-like axis for our starship. This axis represents all the events that take place simultaneously at the present time for the starship. Now, if we take the space-like axis and shift it down a little bit, then we get to set points that are all also simultaneous for the starship, but they happen in the past. Now you might notice that they are on purpose through the present and the past space-like axis for the starship, so that the present axis goes through event A, whereas the past axis goes through event C. Now for the stationary observer, that is the one with the big axis, event A precedes event C. And we can see this because event C is above event A. We can see this explicitly by noting that the space-like axis is a set of simultaneously occurring points that happen in the present. And by shifting the space-like axis upwards, we get a couple axis, which is a set of simultaneous points that happen in the future observer for the big observer. Now, what we call the starship, the one with the black axis. Well, for this observer, event C happens in the past, while event A happens in the present, and therefore C precedes A. Consequently, if there is a causal relation between A and C due to faster light travel, our two observers would be unable to agree whether A causes C or C causes A. For the same argument, suppose that faster light communication is possible, and as event A happens, the people at A emit a faster light beam towards C, causing event C to occur. Now, for the big observer, that is the stationary observer, this sounds okay. Event A precedes event C. The only issue is the signal from A to C travels faster than light. On the other hand, what happens for the moving observer? That is the one with the black axis. Well, for that observer, the tachyon is emitting a Now here is a crazy part. Faster than light travel and tachyons are indeed allowed by Einstein's theories of relativity with general expression. However, as we have shown now, if FTL or tachyon exist, they're going to cause the breakdown of causality or reduce time travel. In short, it appears that nature must decide between whether it wants to have causality or it wants to have faster time travel or tachyons. Now, of course, letting go of causality brings the usual or the standard paradoxes related to time travel, like the one explored in the Back to the Future. Would you go back in time and prevent your parents from having you in the first place? And if they did happen, how could you go back in time to prevent your parents from having you? Again, looking at science fiction towards the answer, there have been proposals to think about multiple timelines, and therefore the implications are eliminated by having a different timeline and different causes and effects. To conclude this video, I will have analyzing arguments for and against faster travel. If faster than light travel is allowed, then where are all the time travelers? And for that matter, where are all the aliens? This is called the Fermi paradox. It is named after Henry Fermi, who mentioned the paradox in lunchtime conversation with his colleagues. Fermi is of course much better known for his discoveries in nuclear reactions, a work for which he received the Nobel Prize. He also constructed the world's first nuclear reactor, which he constructed in a squash form under the stands of the University of Chicago's Stanford Field. To answer Fermi, since we haven't observed any aliens or time travelers, does that mean that faster than light travel is indeed impossible? And its argument is due to Einstein. Einstein basically said, we kind of like causality, let's abandon faster than light travel instead. Now you've probably heard about wormholes. Well, wormholes provide us a way to construct faster than light travel. It turns out that the theory of quantum gravity, which scientists are currently trying to describe, has something to say about wormholes. Now, a wormhole can be thought of as a shortcut through space. So, if one should travel a shorter distance by going around the wormhole through ordinary space. But that raises the question: is a wormhole indeed a shortcut? It turns out that there is an argument by Maltese, one of the key players in constructing the theory of quantum gravity, that no, the route through the wormhole is a longer route than the route around it through regular space. However, quantum gravity is still work in progress, so it's not clear how seriously we should take this argument. What we really need to move forward is a more complete theory, for example, a more complete theory of quantum gravity, which could decide on whether it's possible to have faster than light travel. And even better alternative will be some sort of experiment which could decide the question. For now, while faster than light travel and are not ruled out by science, however, there is no evidence that either exists, at least outside of the domain of science fiction. As always, thanks for watching, and remember to stay curious.
There is a hole at the bottom of math, a hole that means we will never know everything with certainty. There will always be true statements that cannot be proven. Now, no one knows what those statements are exactly, but they could be something like the twin prime conjecture. Twin primes are prime numbers that are separated by just one number, like 11 and 13, or 17 and 19. And as you go up the number line, primes occur less frequently, and twin primes are rarer still. But the twin prime conjecture is that there are infinitely many twin primes. You never run out. As of right now, no one has proven this conjecture true or false. But the crazy thing is this: we may never know. Because what has been proven is that in any system of mathematics where you can do basic arithmetic, there will always be true statements that are impossible to prove. That is life. Specifically, this is the game of life, created in 1970 by mathematician John Conway. Sadly, he passed away in 2020 from COVID-19. Conway's game of life is played on an infinite grid of square cells, each of which is either alive or dead. And there are only two rules. One, any dead cell with exactly 3 neighbors comes to life. And 2, any living cell with less than 2 or more than 3 neighbors dies. Once you've set up the initial arrangement of cells, the 2 rules are applied to create the next generation. And then one after that, and so on. It's totally automatic. Conway called it a zero-player game. But even though the rules are simple, the game itself can generate a wide variety of behavior. Some patterns are stable. Once they arise, they never change. Others oscillate back and forth in a loop. A few can travel across the grid forever, like this glider here. Many patterns just fizzle out. But a few keep growing forever. They keep generating new cells. Now you would think that given the simple rules of the game, you could just look at any pattern and determine what will happen to it. Will it eventually reach a steady state? Or will it keep growing without limit? But it turns out this question is impossible to answer. The ultimate fate of a pattern in Conway's game of life is undecidable, meaning there is no possible algorithm that is guaranteed to answer the question in a finite amount of time. You could always just try running the pattern and see what happens. I mean, the rules of the game are a kind of algorithm after all, but that's not guaranteed to give you an answer either, because even if you run it for 1 million generations, you won't be able to say whether it'll last forever or just 2 million generations, or 1 billion, or a Googleplex. Is there something special about the game of life that makes it undecidable? Nope. There are actually a huge number of systems that are undecidable. Weighing tiles, quantum physics, airline ticketing systems, and even Magic the Gathering. To understand how undecidability shows up in all of these places, we have to go back 150 years to a full-blown revolt in mathematics. In 1874, Georg Cantor, a German mathematician, published a paper that launched a new branch of mathematics called set theory. A set is just a well-defined collection of things. So the 2 shoes on your feet are a set, as are all the planetarians in the world. There's a set with nothing in it, the empty set, and a set with everything in it. Now Cantor was thinking about sets of numbers, like natural numbers, positive integers like 1, 2, 3, 4, and so on, and real numbers, which include fractions like a third, 5 halves, and also irrational numbers like pi, e, and the square root of 2. Basically, any number that can be represented as an infinite decimal. And you wondered, are there more natural numbers or more real numbers between 0 and 1? The answer might seem obvious. There are an infinite number of each, so both sets should be the same size. But to check this logic, Cantor imagined writing down an infinite list, matching up each natural number on one side with a real number between 0 and 1 on the other. Now, since each real number is an infinite decimal, there is no first one, so we can just write them down in any random order. The key is to make sure we get them all with no duplicates and line them up one-to-one with an integer. If we can do that with none left over, then we know that the set of natural numbers and the set of real numbers between 0 and 1 are the same size. So assuming we've done that, we have a complete infinite list with each integer acting like an index number, a unique identifier for each real number on the list. Now, Cantor says, start writing down a new real number. And the way we're going to do it is by taking the first digit of the first number and adding 1. Then take the won't appear anywhere on our list. It's different from the first number in the first decimal place, different from the second number in the second decimal place, and so on down the line. It has to be different from every number on the list by at least one digit, the number on the diagonal. That's why this is called Cantor's diagonalization proof. It shows there must be more real numbers between 0 and 1 than there are natural numbers extending out to infinity. So not all infinities are the same size. Cantor called them countable and uncountable infinities respectively. And in fact, there are many more uncountable infinities which are even larger. Now, Cantor's work was just the latest blow to mathematics. For 2,000 years, Euclid's elements were considered the bedrock of the discipline. But at the turn of the 19th century, Lobachevsky and Gauss discovered non-Euclidean geometries, and this prompted mathematicians to examine more closely the foundations of their field. And they did not like what they saw. The idea of a limit, a part of calculus, turned out to be poorly defined. And now Cantor was showing that infinity itself was much more complex than anyone had imagined. In all this upheaval, mathematics fractured, and a huge debate broke out among mathematicians at the end of the 1800s. On the one side were the intuitionists who thought that Cantor's work was nonsense. They were convinced that math was a pure creation of the human mind, and that infinities like Cantor's weren't real. Henri Poincaré said that later generations will regard set theory as a disease from which one has recovered. Leopold Kronecker called Cantor a scientific charlatan and a corrupter of the youth, and he worked to keep Cantor from getting a job he wanted. On the other side were the formalists. They thought that math could be put on absolutely secure logical foundations through Cantor's set theory. The informal leader of the formalists was the German mathematician David Hilbert. Hilbert was a living legend, a hugely influential mathematician who had worked in nearly every area of mathematics. He almost beat Einstein's punch on general relativity. He developed entirely new mathematical concepts that were crucial for quantum mechanics, and he knew that Cantor's work was brilliant. Hilbert was convinced that a more formal and rigorous system of mathematical proof based on set theory could solve all the issues that had cropped up in math over the last century, and most other mathematicians agreed with him. No one shall expel us from the paradise that Cantor has created, Hilbert declared. But in 1901, Bertrand Russell pointed out a serious problem in Cantor's set theory. Russell knew that if sets can contain anything, they can contain other sets, or even themselves. For example, the set of all sets must contain itself, as does the set of sets with more than 5 elements. You could even talk about the set of all sets that contain themselves. But this leads straight to a problem. What about R, the set of all sets that don't contain themselves? If R doesn't contain itself, well, then it must contain itself. But if R does contain itself, then by definition, it must not contain itself. So R contains itself if and only if it doesn't. Russell had found another paradox of self-reference. And he later explained his paradox using a hairy analogy. Let's say there's a village populated entirely by grown men with a strange law against beards. Specifically, the law states that the village barber must shave all and only those men of the village who do not shave themselves. But the barber himself lives in the village too, of course. He's a man, so who shaves him? If he doesn't shave himself, then the barber has to shave him. But the barber can't shave himself because the barber doesn't shave anyone who shaves themselves. So the barber must shave himself if and only if he doesn't shave himself. It's a contradiction. The intuitionists rejoiced at Russell's paradox, thinking it had proven set theory hopelessly flawed. But Zermelo and other mathematicians from Hilbert School solved the problem by restricting the concept of a set. So the collection of all sets, for example, is not a set anymore. And neither is the collection of all sets which don't contain themselves. This eliminated the paradoxes that come with self-reference. Hilbert and the formalists set to fight another day, but self-reference refused to die quite that easily. Fast forward to the 1960s, the mathematician Hao Wang was looking at square tiles with different colors on each side, like these. The rules were that touching edges must be the same color, and you can't rotate or reflect tiles, only slide them around. question was, if you're given an arbitrary set of these tiles, can you tell if they will tile the plane? That is, will they connect up with no gaps all the way out to infinity? It turns out you can't tell for an arbitrary set of tiles whether they will tile the plane or not. The problem is undecidable, just like the fate of a pattern in Conway's Game of Life. In fact, it's exactly the same problem. And that problem ultimately comes from self-reference, as Hilbert and the formalists were about to discover. Hilbert wanted to secure the foundations of mathematics by developing a new system for mathematical proofs. Systems of proof were an old idea going back to the ancient Greeks. A system of proof starts with axioms, basic statements that are assumed to be true, like a straight line can be drawn between any two points. Proofs are then constructed from those axioms using rules of inference. Methods for using existing statements to derive new statements. These are chosen to preserve the truth. The existing statements are true, then so are the new ones. Hilbert wanted a formal system of proof, symbolic logical language with a rigid set of manipulation rules for those symbols. Logical and mathematical statements could then be translated into this system. If you drop a book, then it will fall would be A then B. And no human is immortal would be expressed like this. Hilbert and the formalists wanted to express the axioms of mathematics as symbolic statements in a formal system, and set up the rules of inference as the system's rules for symbol manipulation. So Russell, along with Alfred North Whitehead, developed a formal system like this in their 3-volume Principia Mathematica, published in 1913. Principia Mathematica is vast, a total of nearly 2,000 pages of dense mathematical notation. It takes 762 pages just to get to a complete proof that 1 + 1 = 2, at which point Russell and Whitehead dryly note, the above proposition is occasionally useful. The authors had originally planned a 4th volume, but unsurprisingly, they were too worn out to complete it. So yes, the notation is dense and exhausting, but it is also exact, unlike ordinary languages. It leaves no room for errors or fuzzy logic to creep in. And most importantly, it allows you to prove properties of the formal system itself. There were 3 big questions that Hilbert wanted answered about mathematics. Number 1, is math complete? Meaning, is there a way to prove every true statement? Does every true statement have a proof? Number 2, is mathematics consistent? Meaning, is it free of contradictions? I mean, if you can simultaneously prove A and not A, then that's a real problem. You can prove anything at all. And number 3, is math decidable? Meaning, is there an algorithm that can always determine whether a statement follows from the axioms? Now, Hilbert was convinced that the answers to all 3 of these questions was yes. At a major conference in 1930, Hilbert gave a fiery speech about these questions. He ended it with a line that summed up his formalist dream. In opposition to the foolish ignorabimus, which means we will not know, our slogan shall be, we will know. These words are literally on his grave.
Мне кажется, что с этим надо завязывать, потому что дальше я буду уже делать лишнее.
Explained that he had found the answer to the first of Hilbert's 3 big questions about completeness. The answer was no. A complete formal system of mathematics was impossible. The only person who paid much attention was John von Neumann, one of Hilbert's former students, who pulled Gödel aside to ask a few questions. But the next year, Gödel published a proof of his incompleteness theorem, and this time everyone, including Hilbert, noticed. This is how Gödel's proof works. Gödel wanted to use logic and mathematics to answer questions about the very system of logic and mathematics. And so he took all these basic symbols of a mathematical system, and then he gave each one a number. This is known as the symbols of Gödel numbers. So not gets the number 1, 4 as the Gödel number 2, if then is Gödel number 3. Now, if you're expressing all of these symbols with numbers, then what do you do about the numbers themselves? Well, 0 gets its own Gödel number 6, and if you want to write a 1, you just put this successor symbol next to the immediate successor of 0 is 1. If you want to write 2, you have to write SS0, and that represents 2, and so on. So you could represent any positive integer this way. Granted, it is cumbersome, but it works, and that is the point of this system. So now that we have Gödel numbers for all of the basic symbols and all of the numbers we might want to use, we can start to write equations. Like we could write 0 equals 0. So these symbols have the Gödel numbers 6, 5, 6. And we can actually create a new card that represents this equation, 0 equals 0. And the way we do it is we take the prime numbers, starting at 2, and we raise each one to the power of the Gödel number of the symbol in our equation. So we have 2 to the power of 6 times 3 to the power of 5 times 5 to the power of 6 equals 243 million. So 243 million is the Gödel number of the whole equation, 0 equals 0. We can write down Gödel numbers for any set of symbols that you can imagine. So really, this is an infinite deck of cards where any set of symbols that you want to write down in a sequence, you can represent with a unique Gödel number. And the beauty of this Gödel number is you can do a prime factorization of it, and you can work out exactly what symbols made up this card. So in this whole pack of cards, there are going to be true statements and there are going to be false statements. So how do you prove that something is true? Well, you need to go to the axioms. The axioms also have their own Gödel numbers, which are formed in the same way. So here's an axiom which says not the successor of any number x equals 0, which makes sense because in this system there are no negative numbers, so the successor of any number cannot be 0. So we can put down this axiom, then we can substitute in 0 for x, saying that 1 does not equal 0, and we've created a proof. This is the simplest proof I can think of that shows that 1 does not equal 0. Now this card, for the proof of 1 does not equal 0, gets its own Gödel number. The way we calculate this Gödel number is just as before, we take the prime numbers, we raise 2 to the power of the axiom times 3 to the power of 1 does not equal 0, and we get a tremendously large number. It would have 73 million digits if you calculated it all out. So I've just left it here in exponential notation. As you can see, these numbers get very large. So you might want to start just calling them by letters. So we can say this one is Gödel number A, this is Gödel number B, Gödel number C, and so on. Gödel goes to all this trouble to find this card. It says there is no proof for the statement with Gödel number G. The trick is that the Gödel number of this card is G. So what the statement is really saying is this card is unprovable. There is no proof anywhere in our infinite deck for this card. Now think about it. If it's false and there is a proof, then what you have just proven is there is no proof. So you're stuck with a contradiction. That would mean the mathematical system is inconsistent. The other alternative is that this card is true. There is no proof the statement is Gödel number G. That means this mathematical system has true statements in it that has no proof. So the mathematical system is incomplete. And that is Gödel's incompleteness theorem. This is how he shows that any basic mathematical system that can do fundamental arithmetic will always have statements within it which are true, but we have no proof. There's a line in the TV show The Office that echoes the self-referential paradox of Gödel's proof.
Jim is my enemy, and it turns out that Jim is also his own worst enemy. The enemy of my enemy is my friend. So Jim is actually my friend. But because he is his own worst enemy, the enemy of my friend is my enemy. So actually Jim is my enemy. But
Gödel's incompleteness theorem means that truth and provability are not at all the same thing. Hilbert was wrong. There will always be true statements about mathematics that just cannot be proved. Now, Hilbert could console himself with the hope that at least we could still prove maths consistent, that is, free of contradictions. But then Gödel published his second incompleteness theorem, in which he showed that any consistent formal system of math cannot prove its own consistency. So, taken together, Gödel's two incompleteness theorems say that the best you can hope for is a consistent yet incomplete system of math. But a system like that cannot prove its own consistency. So some contradiction could always crop up in the future, revealing that the system you've been working with has been inconsistent the whole time. And that leaves only the third and final big question for Hilbert: is mathematics decidable? That is there an algorithm that can always determine whether a statement follows from the axioms? And in 1936, Alan Turing found a way to settle this question. But to do it, he had to invent the modern computer. In his time, computers weren't machines, they were people, often women who carried out long and tedious calculations. Turing imagined an entirely mechanical computer. He wanted it to be powerful enough to perform any computation imaginable, but simple enough that you could reason through its operation. So he came up with a machine that takes as input an infinitely long table of square cells, each containing a 0 or a 1. The machine has a read-write head that can read one digit at a time, that it can perform one of only a few tasks: overwrite a new value, move left, move right, or simply halt. Halting means the program has run to completion. The program consists of a set of internal instructions. You can think of it like a flowchart that tells the machine what to do based on the digit it reads and its internal state. You can imagine exporting these instructions to any other Turing machine, which would then perform in exactly the same way as the first. Although this sounds simple, a Turing machine's arbitrarily large memory and program mean it can execute any computable algorithm if given enough time. From addition and subtraction to the entire YouTube algorithm, it can do anything a modern computer can. That's what made the Turing machine so useful in answering Hilbert's question on decidability. When a Turing machine halts, the program has finished running and the tape is the output. But sometimes a Turing machine never halts. It gets stuck in an infinite loop. Is it possible to tell beforehand if a program will halt or not on a particular input? Turing realized this halting problem was very similar to the decidability problem. If he could find a way to figure out if a Turing machine would halt, then it would also be possible to decide if a statement followed from the axioms. For example, you could solve the twin prime conjecture by writing a Turing machine program that starts with the axioms and constructs all theorems that can be produced in one step using the rules of inference. Then it constructs all theorems that can be produced in one step from those, and so on. Each time it generates a new theorem, it checks if it's the twin prime conjecture. And if it is, it halts. If not, it never halts. So if you could solve the halting problem, you could solve the twin prime conjecture and all sorts of other unsolved questions. So Turing said, let's assume we can make a machine H that can determine whether any Turing machine will halt or not on a particular input. You insert the program and its input, and H simulates what will happen, printing out either halts or never halts. For now, we don't worry about how H works. We just know that it always works. It always gives you the right answer. Now, we can modify the H machine by adding additional components. One, if it receives the output halts, immediately goes into an infinite loop. Another, if it receives never halts, then it immediately halts. We can call this entire new machine H+, and we can export the program for that entire machine. Now, what happens if we give this machine its own code simulating what H plus would do given its own input. Essentially, H has to determine the behavior of a machine that it itself is a part of in this exact circumstance. If H concludes that H plus never halts, well, this makes H plus immediately halt. If H thinks H plus will halt, then that necessarily forces H plus to live. Whatever output the halting machine H gives, it turns out to be wrong. There's a contradiction. The only explanation can be that a machine like H can't exist. There's no way to tell in general if a Turing machine will halt or not on a given input. And this means mathematics is undecidable. There is no algorithm that can always determine whether a statement is derivable from the axioms. So something like the twin prime conjecture might be unsolvable. We might never know whether there are infinite twin primes or not. The problem of undecidability even crops up in physical systems. In quantum mechanics, one of the most important properties of a many-body system is the difference in energy between its ground state and its first excited state. This is known as the spectral gap. Some systems have a significant spectral gap, whereas others are gapless. There are a continuum of energy levels all the way down to the ground state. And this is important because at low temperatures, gapless quantum systems can undergo phase transitions, while gap systems cannot. They don't have the energy needed to overcome the spectral gap. But figuring out if the system is gapped or gapless has long been known to be a very difficult problem. Only recently, in 2015, did mathematicians prove that in general, the spectral gap question is undecidable. To quote the authors, even a perfect, complete description of the microscopic interactions between a material's particles is not always enough to deduce its macroscopic properties. Now remember that Turing designed his machines to be as powerful computers as it is possible to make. To this day, the best computational systems are those that can do everything a Turing machine can. This is called Turing completeness. And it turns out there are many such Turing complete systems. Although they are powerful, every Turing complete system comes with a catch, its own analog of the halting problem, some undecidable property of the system. Wang tiles are Turing complete. Their halting problem is whether or not they'll tile the plane. Complex quantum systems are Turing complete, and their halting problem is the spectral gap question. In the game of life, Turing complete, its halting problem is literally whether or not it halts. There are many more examples of this, like airline ticketing systems, Magic the Gathering, PowerPoint slides, and Excel spreadsheets. Nearly every programming language in existence is designed to be Turing complete. But in theory, we only need one programming language because we can program anything at all using any Turing complete system. So here's a Turing machine inside the game of life. And since the game of life is itself Turing complete, it should be capable of simulating itself. And indeed, it is. This is the game of life, running on the game of life. The real legacy of David Hilbert's dream is all of our modern computational devices. Kurt Gödel suffered bouts of mental instability later in life. Convinced that people were trying to poison him, he refused to eat. Eventually, starved himself to death. Hilbert died in 1943. His epitaph was his slogan from 1930. We must know, we will know. The truth is, we don't know. Sometimes we can't know. But in trying to find out, we can discover new things, things that change the world. Alan Turing put his ideas about computing to practical use in World War II, leading the team at Bletchley Park that built real calculating machines to crack Nazi codes for the Allies. By one estimate, the intelligence Turing and his colleagues gathered from decrypted messages shortened the war by 2 to 4 years. After the war, Turing and John von Neumann designed the first true programmable electronic computer, ENIAC, based on Turing's designs. But Turing didn't live to see his ideas develop much further. In 1952, the British government convicted him of gross indecency on learning he was gay. He was stripped of his security clearance and forced to take hormones. In 1954, he committed suicide. Turing changed the world. He is widely considered to be the most important founding figure in computer science. All modern computers are descended from his designs. But Turing's ideas about computability came from his concept of the Turing machine, which came from thinking about Hilbert's question, is math decidable? So Turing's code-breaking machines, and indeed all modern computers, stem from the weird paradoxes that arise from self-consciousness. There is a hole at the bottom of math, a hole that means we will never know everything with certainty. There will always be true statements that cannot be proven. You might think this realization would have driven mathematicians mad and led to the disintegration of the entire mathematical enterprise. But instead, thinking about this problem transformed the concept of infinity, changed the course of a world war, and led directly to the invention of the device you're watching this on right now. Hey, this video is sponsored by Brilliant, a website full of interactive courses and quizzes that delve deep into topics like math, physics, and computer science. Now, if you've gotten this far into this video, you're likely someone who would love Brilliant. I've been going through their logic course, and it's really got me thinking. The problems start out easy, but get more and more challenging as you develop your understanding. That's what I love about this site. I love how it guides you, not by telling you exactly, but by exposing you to increasingly sophisticated puzzles. And at the end, I feel like I've worked it out for myself, which essentially I have, through their carefully curated selection of problems, and with helpful hints and explanations for when I get stuck. Now, there were a lot of things I wanted to include in this video, but couldn't because it's already over half an hour long. So if you want to explore these ideas further, I'd highly recommend their courses on number theory and computer science fundamentals. For viewers of this channel, Brilliant are offering 20% off an annual subscription to the first 200 people to sign up. Just go to brilliant.org/Veritasium, and I will put that link down in the description. So I want to thank Brilliant for sponsoring Veritasium, and I want to thank you for watching.
Hello, today I'm going to try to derive the Einstein field equations. This will be a basic introduction. It won't be rigorous, it will cover the essence, but it will still be quite complex. If you want more detail, then I refer you to Professor Leonard Susskind's excellent lectures that he gave from October to December 2008 at Stanford. I've put a link to the YouTube version of these lectures in an annotation on this video. I am going to follow his approach so that it will be familiar to you, but I shall do it in a much more simplified version. And let's always remember that it took Einstein 10 years to develop these equations, and he had access to many maths professors on the way. As usual, I'm making the assumption that you understand calculus and basic geometry, and that you've also seen or are aware of the information in my general relativity videos that are already up on YouTube, and in particular that you're aware of two key points. The first is what is called the principle of equivalence. What that says is that if you are in a box with no windows, then you cannot tell the difference between being in outer space and accelerating with an acceleration g, or being in the same box on the surface of the Earth, stationary, but subject to the gravitational force, which carries an acceleration g. There is no experiment, that's what you in the box, there is no experiment that you can do that will distinguish between those two situations. Now that is actually not quite true. The difference, of course, is that if you are in outer space, traveling with an acceleration varies according to the height above the Earth, the value of G at this point will be ever so slightly greater than the value of G at this point. So there is a slight difference in the value of G in this situation. And if you can measure that, then you can tell the difference. That difference is called the time pulse. But apart from that, Einstein said that that was a principle of equivalence. You can't tell the difference whether you are accelerating at G or subject to a gravitational force, which is represented by the acceleration G. The second principle is that light bends in a gravitational field. This was Einstein's reasoning. If you take the person who is in the box that is accelerating through space with an acceleration G, box. And this time we're going to shine a light from this side of the box to the other side of the box. But of course that will take a finite time, albeit small. And if this box is accelerating with an acceleration G, by the time the light gets halfway across, the box will have accelerated a little bit further forward. So it will now be here, which means the light will have reached that position there. By the time the light gets to the right-hand side, the box will of course have accelerated still further. And now, the light, which of course is just going in a straight line, will reach here. So if you look at it, it appears within the box that the light has gone from here to a point lower down, to a point even lower down. In other words, the overall impression is that the light has gone from here to here to here, and that's a curve. At least it should be if I call it properly. So Einstein says, if that is what happens when you are accelerating through space with acceleration G, since the principle of equivalence says you can't tell the difference between that and being stationary on Earth subject to an acceleration G, then the same thing should happen in this scenario here, that light will appear to bend in a gravitational field. Now, of course, he could have been wrong, but in fact this was shown to be true during a solar eclipse. What happens during a solar eclipse is that the moon essentially blocks the sun, so that from the Earth, the sun, as it were, is blotted out. And what was noted from the position on Earth was that they could see a star just slightly to the right of the sun. But they knew, astronomers knew, that that star actually was located behind the sun, and it shouldn't have been possible to see it. And the explanation was that what was actually happening was that light from that star was being bent in the gravitational field of the sun, and then coming to us on Earth, giving the impression that the star was here, but in fact the star was really here, but the light was being bent in the sun's gravitational field. Now, here was the problem for Einstein. Newton's law of gravitation, which everybody had thought had served us well for so long, says that the gravitational force is equal to the gravitational constant times the mass of one body multiplied by the mass of another body divided by the distance between them, r squared, divided by the distance squared. And that's fine, except that in this situation here, light is bending in a gravitational field, but photons of light have no mass. So these two mass terms, or at least the sun has mass, but the photon doesn't. So this form of Newton's law doesn't work if it is going to apply to light, like photons have no mass. So Einstein came up with a completely different approach to gravity. Instead of there being gravity, actually what is happening is that all forms of motion are represented by movement in curved space-time. And I can illustrate that in this way. Let's suppose that we take a trampoline. This is the surface of the trampoline. And that's representing space-time. We put a small marble on that the marble will have virtually no effect. It might make a very tiny indentation on the trampoline. But now let's suppose I get on the trampoline. If I get on the trampoline, with my weight, the trampoline is going to bend quite substantially. And that is the equivalent of bent space-time, curved space-time. What's going to happen to this marble? Well, the marble is now going to fall towards me. The analogy is not brilliant, but it'll do for our purposes. Now, Newton said that that movement towards me was caused by gravitational attraction. Einstein, on the other hand, says what is happening is the marble is moving along the shortest path in curved space-time. So that when the Earth goes around the Sun, there's the Sun, and here's the Earth in a reasonable circular orbit going around the Sun. Newton says that there's a gravitational force between the Sun and the Earth, which provides the centripetal force that keeps the Earth in orbit. Einstein says, no, that's not it at all. What happens is the Sun being massive, curves space-time, and the Earth is simply going round that curve in a straight line in curved space. Now, you might be wondering two things. Firstly, what is space-time? And secondly, why did Einstein think that it would be curved? Well, space-time is really just space and time all thought of as one set of coordinates. We usually think of space as having three dimensions, which we represent by three what are called orthogonal axes. They are at right angles to one another. So we normally have the x-axis, the y-axis, and the z-axis, or if you like, we have three dimensions in space, up and down, back and forth, and side to side. If you add time to that, you get four-dimensional space-time. Four-dimensional space-time is very different.
Попробуем поиграться белым.
We can only conceive three dimensions. So I'm going to cheat, and I'm going to draw one dimension of time and one dimension of space, which is the x-axis. I could, of course, draw another dimension this way, but I'll just leave it as one dimension of time and one dimension of space. Now, if you draw a constant velocity in space-time, you get a straight line, because a straight line is distance divided by time. It's a constant distance divided by constant time, and that is a constant velocity. But if you accelerate it in space-time, you get a curve. The reason, of course, being that acceleration means that the longer the time, the further you go. So there is a curve in the acceleration. And because gravity causes acceleration, it causes a graph which is curved in the space-time coordinates. Einstein's view was that therefore, in some way, space-time must be curved if it is creating an acceleration which has the effect of creating a curve in those space-time coordinates. Well, that's the end of the introduction, so now it's time to introduce you to the Einstein field equations that we're going to try to derive. And there they are. You may observe that there is only one equation, but in fact that's not true, because you will notice that there are some indices, mu and nu, which lies in several places in the equations. Now, mu and nu represent the dimensions of space-time. 0, 1, 2, and 3. 0 is time, 1 is the x-axis, 2 is the y-axis, and 3 is the z-axis. So mu and nu can each take 4 values between 0 and 3. And the combination of mu and nu means that there are 16 variations of this equation, with mu and nu having numbers between 0 and 3. You might therefore think that there are 16 equations in 4-dimensional space-time, but in fact 6 of them are duplicates. So in fact it reduces to 10. So you are looking at 10 Einstein equations. Now what all all these hieroglyphics mean? Well, you'll be pleased to know that some of them you already know. You will know what a half is, you know what 80 is, you know what pi is. G is the good old-fashioned gravitational constant, and C is the speed of light. So there are only a few things that we need to sort out. First, we've got this peculiar term R mu mu, which is called the Ricci curvature tensor. We'll derive that. Then in two places, we've got this term G mu mu. G mu mu is the metric tensor. We'll derive that. Then we have R, but with no indices. That's called the curvature scalar. We'll show what that is. Then we've got capital lambda, which turns out to be the cosmological constant. We'll explain the reason for that. And finally, we've got T mu mu, which is the stress energy momentum tensor. And we'll try to explain what that is. Now, the whole point about this equation is that it balances two things. Everything on the left-hand side refers to curvature of space-time. Everything on the right-hand side is to do with mass and energy. And as some people have sometimes helpfully said, that what Einstein's field equations basically say is that mass tells space-time how to curve, and curved space-time tells mass how to move. So here's our agenda for the remainder of this video. We've done the introduction. Next, we shall do metric tensors. Then we'll move on to Christopher's, which are capital gamma terms. You may wonder why I need to do that, because they don't appear to feature in the Einstein field equation, but they are heavily involved in the Ricci curvature tensor, so we'll need the Christopher's involved. Then we'll look at curvature itself, which will enable us to derive the Ricci curvature tensor and the curvature scalar. Then we'll look at the stress energy momentum tensor, and then the cosmological constant, and finally we'll put it all together. You may want to take a break through this video just to collect your thoughts. Indeed, before we move on to the next section, you might fancy a break now. Okay, part 2, the metric tensor. We're going to consider a field. We could consider any field, a magnetic field, an electric field, a temperature field. I'm going to consider one of the most basic fields of all, a field with grass where the cows graze. Here is my field, and it's going to be a very bumpy field. There are hills all over my field, and here am I standing on one of the hills. And the value of the field is going to be the height above sea level. We usually give field value 5. And everywhere you'll agree in my field, there will be a height above sea level that I can measure. And that height will constantly change because my field is a very bumpy field. Now, how do I know where I am? Well, I can impose a set of coordinates. Here's my x coordinate, here's my y coordinate, and I am then at that position on the x coordinate, and that position on the y coordinate. It's a bit like a map reference. So I uniquely define my position, and for every position I take, I can find a value of phi, which is essentially the height above sea level of my position in the field. The question I now want to ask is, how does that height change if I move a little bit? And you should immediately respond that it depends on which direction I move. The reason for that is, let's suppose that part of the field consists of a ridge. Now, a ridge is something where the slope goes down on one side and down on the other side, but along the top it's flat. So if I'm standing on the top of the ridge and I move, let's say this is the x direction, if I move in the x direction, I go down the ridge quite substantially. But if I go in the y direction, let's say that's the y direction, I'm I'm just walking along the top of the ridge, and that's flat. So direction of movement is important. In the X direction, I will drop considerably. In the Y direction, I stay on level ground. Now, how can I tell by how much the height will vary as I move along? Well, let's consider a gradient. Here is a gradient, which I'm going to call a 1 in 10 gradient. What that means is that for every 10 meters that I walk along, I will drop 1 meter. So if I start here and I walk 10 meters, by the time I get to the end, I have not only walked 10 meters along, I have dropped 1 meter down. The way you would describe that mathematically is you would say that the change in height as I walk along is equal to the gradient, which we express as the phi by the x, the rate of change of height with distance. That's what 1 in 10 is. Rate of change of height with distance multiplied by the distance you actually walk, dx. Let's just try that for a moment. The change in height will equal the gradient. Well, I told you what the gradient is. It's 1 in 10. And let's say I walk 5 meters, so that the distance dx is 5 meters. That means that the phi will equal 5 over 10, which of course is a half a meter. So what we've just calculated is that if you walk 5 meters along a 1 in 10 gradient, your height changes by half a meter. But this is the general form. Change in height, change in the value of the vehicle is equal to the gradient multiplied by the distance you travel. Now, clearly, in my field, I'm not going to have clear gradients like this because it's a very bumpy and irregular field. But over a very, very small distance, which is why I put dx and d phi, that will be true. But as I said, direction matters. So consequently, one would have to say that the change of height, if you're traveling in the x direction, is equal to the gradient in the x direction, multiply the distance, multiplied by the distance you walk in the x direction. Or you could also say that the change in height in the y direction is equal to the gradient in the y direction, multiplied by the distance you walk in the y direction, which is fine. And these two gradients will not, of course, be the same. If we were on the ridge, this would be a very steep gradient in the x direction, but there would be a level gradient in the y direction. Of course, I may not want to walk in just the x or the y direction. Let's suppose that instead of walking in x or y direction, I want to simply walk in that direction, just to be awkward. Well, of course, that is simply a combination of walking in the y direction and walking in the x direction. And in fact, we can regard these as vectors. And in my video on the manipulation of vectors, I showed that when you want to add vectors together, you do it by a tip-to-tail process. So that in fact you take these two vectors, dy and dx, and you put them tip-to-tail. It doesn't matter which way you do it. So let's take dx. It's like that. Then dy goes to the tip of the x vector, matches the tail of the y vector. So this is dx. This is dy. And then the resultant is the tail of the first and the tip of the last. So that becomes the resultant vector, which we call ds. And we can use Pythagoras to work out what ds is. Of course, ds squared is equal to dx squared plus dy squared. That, of course, is very useful. If you want to add the vectors together, that gives you, this is the magnitude. But for purposes of adding the vectors together, we simply say that ds, with a line above it to indicate that it's a vector, is equal to dx plus dy. Or, if we want to know what the change in height is, we can say that the change in height as we go along the path S is equal to the change in height as we go along the path X plus the change in height as we go along the path Y. two terms here, dx, d phi x and d phi y, we calculated up here. That's what these two terms say. So I'm going to substitute these values into this formula here. And that will give me that d phi s is equal to, now for d phi x, I'm going to replace that by the gradient times the distance. And here I'm going to replace this by the gradient, but this time in the y direction times the distance in the y direction. And to be absolutely proper about all of this, what I should actually write is I'm going to give these gradient terms curly d's. And the reason I'm going to do that is because that's what's called a partial derivative. It simply indicates that although this is the derivative with respect to x, there are other derivatives, in this case a derivative with respect to y. It's not the only derivative. So it's called a partial derivative, and it's indicated as a partial derivative by virtue of having a curly d. Now I want to pause for a while I do a nomenclature change, and I promise you it won't hurt. Up to now, I have been using the coordinates x and y. I am now going to change them. Wherever I have used x before, I'm going to call that x1. And wherever I have used y before, I'm going to call that x2. Why do I do that? Well, for 3 dimensions in space, we typically use x, y, and z as our coordinates. Suppose I needed another coordinate. What letter am I going to use? There isn't one after z. I could, of course, find another spare letter, but letters of the alphabet tend to be used for different purposes in physics, and it becomes very confusing. Whereas if I relabel these x1, x2, and x3, if I need another coordinate, it's a piece of cake. It's x4. Indeed, I can even have an x0, which I will actually use for a time coordinate. If I need further dimensions of space, I can have x4, x5, x6, and so on. There's no limit. So, firstly, changing the coordinates in this system means I've got an unlimited number of coordinates if I need them, dimensions of space. Secondly, it releases the y system, which I'm going to use for a different purpose a bit later on. So now I'm going to rewrite this equation here in my new coordinates, simply replacing x by x1 and y by x2. They're exactly the same, but just called them by different names. So if I do that, I will get the d phi, which is the overall change in height as far as my field is concerned, is going to be equal to the gradient, which is defined by the x, now that's the x1, times the distance I moved, the
Так,
plus the
блин,
gradient
конечно,
of the y direction, which is now the dx2 direction, times the distance I moved in the x2 direction. And of course, I could add further terms.
белый краска, к сожалению, очень жидкий.
As many as I need. I'm only going to work in 2 dimensions to keep it simple. And I think you'll see that this equation here can be simplified by saying that the phi is equal to the sum over n of the gradient d phi by the n, sorry, d phi by the x n multiplied by the, you get this term here. And the sum term means you just add them together. So this is a very handy way of summarizing the change in the value of v according to all of these values. And you notice that n is the summation term. You have to do this for all values of n. Here, I'm only having 2 dimensions. However many dimensions you have, you need that number of terms. And I'm going to call that equation number, you can see that, let's just write that again, equation number 1. And I'll put a box around it so that when we refer to it later, we'll be able to spot it. Now here comes the general problem with relativity, be it special relativity or general relativity. Any rules that you come up with must be independent of the frame of reference that you're using to make the observation. In my videos on special relativity, which I will refer to during the course of this presentation, we show that different observers measure different distances and different times depending on their relative velocity. That was called length contraction and time dilation. So if you want to have something that is going to be universally true, you have to make sure that it is true in all reference frames. So when I took my field, where I was standing on the hills, and I put myself at position P, I set a coordinate system, which I call the XY coordinate system, but subsequently renamed X1, X2. And I said that was my map reference, X1 and X2, to find my position. But somebody else could come along and create another set of coordinates, which we will call Y1 and Y2. And now P, of course, I haven't changed my position, I'm still standing on the hill at position P. But as far as the Y frame of reference is concerned, the coordinates are quite different. Y1 and Y2 are quite different from X1 and X2, even though I'm at the same place. And you'll notice that if I want to express Y1 in terms of X coordinates, I have to express it both in terms of an X1 coordinate and an X2 coordinate. In other words, the Y1 position for my point P is actually made up of an X1 and an X2. So the question then that we have to come up with is, if I know all the gradients, which remember we described as dphi by dxn, in the X frame of reference, how can we find all the gradients in the Y frame of reference? And more to the point, how can we relate the two? And for this, we use what's called the chain rule. We say that dphi by dy, and I'm going to pick the y1 coordinate. Pick y2 down, this will pick y1. That is equal, according to the chain rule, that's equal to dphi by the x1 times the x1 by the y1 plus dphi by the x2 times the x2 by the y1. You notice we're only ever sticking to the y1 coordinate, but we sum over the x2 coordinates. Because remember I said that in order to identify the y1 coordinate, you need to know all of the other x coordinates. This can be summarized as dphi by dy, and now I'm going to call this dy n, because it could be any, it could be 1 or 2.
И мне кажется, что мне на нем нужно закончить вот на этом моменте.
Let's just look at this and compare it to this. What I've done is I've put the general value of n in for y. Here I just have y1, but it could have been y2. You have to pick which one you want. It's either 1 or it's 2. But m is a summation term. You sum over n. When n is 1, you get that term. When n is 2, you get that term. This is going to be equation number 2, and I'll put a box around that as well. But let me just repeat and emphasize. N is the value you choose. It's either y1.
Так, ну что из этого могу сказать? Черная краска. Венгерского производства Лапарт казалось намного лучше. Надо попробовать их белую краску. Может быть, она тоже будет плотней. Потому что, конечно, мне немножко сейчас не понравилось, как мне пришлось.
something
Ну,
that has magnitude
конечно,
but no
справится.
direction. Temperature would be a good example of a scalar. It
Вот
just has a value. 32
такая вот
degrees
история.
centigrade. A scalar
В принципе, мне понравилось. То есть, в общем-то, конечно, сделаю что-нибудь похожее, но сделаю вот честно.
has magnitude and direction. So it has a length and it has a
Ну,
direction.
вообще, конечно,
Described in the angle, in this case, with the x-axis. The vector is
решил ошибка сильно не уплотнить.
on rank 1. And how does the
Шелковая бумага.
vector well, we can use
Должно
the
быть
equation
другое
1
ощущение.
earlier, which is showing on the screen, so you recognize it. And we just
Ладно, всем спасибо за внимание.
so that instead of the y and the x, we replace it by the vectors themselves. So we would simply say that the vector